So I'd now like to invite Neil Fraser, University of the Highlands and Islands, to speak about the North Atlantic circulation and ocean currents. So I'm quite looking forward to this one, actually. I'm sure there's a lot of interesting things going on in the depths of the ocean, which are completely missing to our everyday experience. So I'll be very interested to hear what's going on. Neil, over to you.
Yeah, so thanks very much, David, and thanks a lot for inviting me. Changing oceans in a changing climate. So this is an attempt I'm going to make just to try and summarize some of the recent developments in ocean physics that we're doing in Scotland, UK, and worldwide, and its relation to climate. And I'd just like to thank some of my colleagues who helped me put these slides together as well. So I'm going to start off by asking, what is going on in the North Atlantic? Whoops, went too far. What is going on in the North Atlantic? So the surface temperature in the North Atlantic is warming at below the global average. And this can be seen if we look at this map here. And I saw that Gabby actually showed this, this figure in her talk. This is the warming relative to average global warming, if you like. So the darker reds here are places which are warming above the global average, whereas the pale colors are places that are warming below the global average. And the blue is actually places that are cooling. So the most eye-catching thing about this is this big cold blob in the middle of the North Atlantic. It's really the only place in this map that isn't warming. So we want to know what's going on. Another feature of the North Atlantic is that over the last 100 or 150 years or so, the temperature has been varying on about a 70-year timescale. So this is seen in this figure in the bottom right. This shows the change in sea surface temperature averaged over the entire North Atlantic region. And this is the detrended change. So this is without the long-term climate signal. This is a kind of this signal is on top, if you like. This is a change which is happening on top of the long-term change. So we go through these kind of warm, then cool phases in the North Atlantic. And we want to know why this is happening. We want to understand what makes North Atlantic temperature change, because it has a direct effect on the weather patterns on the surrounding continent. So the North Atlantic temperatures have been linked to the devastating summer heat waves over Europe. It's also known to affect the frequency and the severity of the Atlantic hurricanes, and also has a big influence on rainfall over North Africa. So we really want to understand why the temperature in the North Atlantic is changing and what it's going to do next. So you might see this figure and think, well, is that to do with, you might have heard in the media this idea, oh, the Gulf Stream is slowing down, or is the Gulf Stream is going to collapse? So that's a possible candidate. This also changes in the currents, like the Gulf Stream, could possibly be responsible for this behavior that we see here, this 70-year cycle. But there's a bit of a debate about what causes this. Some people are saying this is caused by aerosol versus CO2 forcing, and then others arguing that it can be explained by volcanic eruptions. But so to go back to the Gulf Stream, when people talk about the Gulf Stream slowing and the Gulf Stream weakening, that's not entirely wrong, but for us as ocean physicists, it's a little bit imprecise. So we prefer to talk about this thing called the Atlantic Meridional Overturning Circulation, so or AMOC. So this is the system of currents whereby warm and salty waters near the surface of the Atlantic are transported northwards, and the Gulf Stream plays a major role in this here. And when these warm and salty waters get into the sort of subarctic, subpolar regions, they cool down a lot due to the atmosphere, and they become cold, salty waters. And when water is both cold and salty, it becomes very dense, so it sinks. And in fact, the dense waters produced here are some of the densest in the global ocean. They sink down and then they flow southwards again at depth. So that's how the AMOC works. I'm going to just break down this acronym a little bit further. So the first word, Atlantic, a little bit self-explanatory. It happens in the Atlantic, but actually there's a more subtle point to be made here. This is a unique feature of the Atlantic, and it doesn't occur, at least not nearly to the same extent, in the Pacific or Indian Oceans. And that's because the Atlantic is a very salty ocean. So it has the high salt content, and it also has these high latitudes required to make this process occur. The second word, meridional, this just means north-south. So the water carries heat and carbon in the kind of north-south direction, as opposed to the east-west direction. So meridional as in along meridians. If you think of the Greenwich meridian runs north-south. And we can see the impact this has if we look at this figure on the right, which is the hemispheric asymmetry of temperature. So along the bottom here, this is latitude going on the left, the South Pole, up to the equator in the middle, then up to the North Pole. And as we go up from the bottom, up the side here, we start off at 1,000 meters depth in the ocean, go up to the ocean surface, and then we go up through the layers of the atmosphere. And the colors show the difference in temperature between the northern hemisphere and the southern hemisphere. And what we can clearly see is that the northern hemisphere is considerably warmer than the southern hemisphere. And it's about 4 degrees on average. And this is really due to the AMOC, in large part due to the AMOC pumping heat northwards through the Atlantic. The next word is overturning. This just describes the shape of the circulation, if you like. So this is described, the AMOC is also described as the ocean conveyor belt. So it's just the way that the water goes along the top, then sinks down, then goes back down and backwards again underneath. So kind of like a conveyor belt or a kind of like a treadmill. And then finally, circulation, well, that just means that the movement of a fluid. And a couple of quick AMOC facts here, just to show you how important it is. So the AMOC carries around 20 million cubic meters of water around per second. And that's around 100 times the amount of water that is being discharged from the Amazon River. It's so big, in fact, that we don't tend to use the unit million cubic meters per second. We have our own shorthand unit for that in oceanography, which is just the Sverdrup, which is 1 million cubic meters per second. And that's named after a pioneering Norwegian oceanographer called Harald Sverdrup. The second fact I'm going to give you is how much heat the AMOC carries. It carries 1.25 petawatts of heat. So 1 petawatt is 10 to the power 15 watts. That's 1 with a 15 zeros after it. So a huge amount of heat. In fact, it's over 60 times human global energy consumption. So hopefully I've convinced you that the AMOC is important. It's carrying a huge amount of water around and a huge amount of heat around. And if it were to weaken or to collapse, it would have a devastating effect on the climate. So we are measuring the AMOC in a few places using these transatlantic transatlantic cross sections. And these are done using kind of a mixture of ship-based surveys, hydrographic moorings, and in some cases we even use little underwater robots which swim around and measure the flow. So I'm going to just pick out a couple of these here. The Rapid Array at 26 North is the longest running and perhaps the most comprehensive record of the AMOC. It's been running since 2004. And we can see here, this is the strength of the AMOC in Sverdrups over time. And over the first few years of the Rapid Array, they saw significant weakening of the AMOC, which caused great concern. However, over the last 10 years or so, the AMOC at Rapid has kind of leveled off and is even maybe potentially starting to increase a bit again. Up in the subpolar regions, we have this OSNAP section, and this runs from Canada across to Greenland, then Greenland across to Scotland. And this is what we work on at SAMS in Oban. We manage the kind of eastern portion of this section. And again, we can see this has been running since 2014, and we can see the strength of the AMOC in this time. This is the black line here in Sverdrups. Again, there's no real trend over this time. What the OSNAP array has allowed us to do, though, is to divide the section up into a western part and an eastern part, east and west of Greenland. And this orange line shows that the eastern part is really what's dominating the signal here. So this tells us that it's dense water formation east of Greenland that is the real driving force behind the AMOC. Now, while these observational campaigns have completely transformed our understanding of how the AMOC works, they are still a little bit short to tell us about what the AMOC is doing on kind of climate change timescales. You know, how has the AMOC been affected since the onset of the industrial era? So what we do in this case, one way that this is tackled is by looking at proxies for the AMOC. So AMOC proxy records, these are not direct measurements of the AMOC, rather they are measurements of some variable that is thought to be representative of the AMOC and you know, thought to closely correlate with the AMOC. So for example, ocean temperature, this line here was a proxy reconstruction of the AMOC by Caesar et al. It's also repeated a few times here, the same color. And they used ocean temperature. What they did was they looked at simulations of the ocean, and they found that in those simulations there were points where the ocean temperature correlated very highly with the strength of the AMOC. And they said, well, in that case, I know what the temperature in that location was doing in real life. So let's assume that could tell us something about what the AMOC was doing in real life. And there's other proxies, and a similar approach has been used. People have looked at corals, people have looked at marine sediment cores and Greenland ice cores to do similar things. And they're kind of compiled here by this Caesar et al. Paper looking at several of the proxies over the last 100 years. And there's a kind of coherent signal amongst the proxies. They all seem to suggest the AMOC has been weakening over the last 100 years. However, there's a large spread in the precise behavior of the AMOC. They don't all look exactly the same. Over multi-decadal timescales, so kind of 20 to 70 year timescales, there's a bit of disagreement over, you know, exactly what the AMOC's been doing. So, well, what I'd suggest is, you know, while these signals make it absolutely clear that there's been, you know, dramatic changes to the climate of the North Atlantic region in the last 100 years, there are still questions remaining over exactly how well these proxies do represent the AMOC. They're not as good as direct measurements. Another way we can look at the past AMOC is by looking in climate models. So this is the AMOC over the last 150 or so years from the state-of-the-art CMIP6 models, which were run in preparation for the latest IPCC report. So teams all over the world ran these different models, and they all got these different answers for the AMOC. Now, you can see there's a huge spread in what the models are saying the AMOC has been doing, you know, historically. In fact, the AMOC, I think, is one of the things that these models really struggle to get right. So, for instance, some of these models are saying the AMOC is around 8 sverdrups, whereas there's one here saying that it's more like 32 sverdrups, and that's a 4-fold increase. To look at, to sort of summarize, what we do is we take the average of all the models, and that's this thick black line here. Well, this really looks quite different to the behavior from the proxies. We don't see strong AMOC weakening over the last 100 years or so. In fact, it's fairly level. In fact, there's a slight increasing trend in AMOC from the models. But you know, it's a little bit problematic. It's the best method we have, but taking the average of all these different models where there's such a huge spread in the strength and the signal in the AMOC that most of them basically have to be wrong. So we're taking the average here as a way of hopefully getting something resembling the truth. But what models can do, which proxies or observations can't do, is tell us about the future. So this is these same models and their projection of the AMOC over the next century. And now we see a much more coherent picture. So virtually unanimously, all the models are suggesting that we'll see significant AMOC weakening over the next century. And perhaps dishearteningly, they're predicting we'll see significant AMOC weakening even in low emission scenarios. It will make a difference to cut down emissions, but we can expect strong AMOC weakening regardless. That's what the models are telling us here. And this seems to be a robust feature across models. So these questions here kind of summarize, do the models and proxies agree on 20th century AMOC behavior? No, the models don't agree with the proxies because the models don't see any weakening, whereas the proxies do. But also there is a great deal of disagreement amongst the models and a degree of disagreement amongst the proxies. Has the AMOC started weakening? Well, I don't think it's that clear. The observations at OSNAP and RAPID don't really see it. It could be that this downturn we're seeing here in the last 10 years of the simulations is kind of the start of a longer term decline in trajectory of the AMOC weakening. But should we be concerned about the AMOC weakening in future? Well, yes, we absolutely should. That's what the models are saying. It's very likely to weaken in future. Now, one of the points raised in the latest IPCC report about the AMOC was that since the previous report, our confidence in our ability to predict the AMOC has increased. On the other hand, our confidence in our understanding and our knowledge of historical AMOC has actually decreased. So in a sense, we now know less about the AMOC in the past than we used to. So there's high uncertainty in what the AMOC was doing in the past. So it's therefore very important that we try to do as good a job as possible to recreate this historical AMOC and use that to get these models running correctly. So I'm going to that's something that we've been doing at SAMS. I'm going to talk a couple of slides about that. So reconstructing past ocean currents. How do we reconstruct past ocean currents? Well, we're going to require a short crash course in oceanography and how oceanography works. So ocean currents are driven by both a barotropic and a baroclinic component. And I'm going to define those two words now. So barotropic flow is due to gradients in the sea surface height. So if we imagine an ocean like this, where the sea surface is tilted, the water where the surface is higher is going to be under higher pressure, and the water wants to flow from high to low pressure. So this is the kind of current, this is what we see, this is a barotropic current driven by a gradient in sea surface height. The water is trying to flow to the left here. We also have baroclinic currents, and these are due to gradients in density. So the oceans are also stratified. So we have light layers sitting on top of denser layers. And if the interface between these layers is tilted, then we'll get this kind of situation where, in this case, the light water wants to flow to the right and the dense water to the left. And they're trying to balance out this tilt, trying to flatten out this tilt. So this is baroclinic flow. And the point is we need both of these if we want to reconstruct currents historically. However, we've only been measuring sea surface height using satellites. That started in 1993. Sort of proper global coverage of sea surface height measurements with satellites began in 1993. On the other hand, we've been measuring the density of the ocean for over 100 years. And this is through our measurements of the temperature and the salinity of the ocean, which you can use temperature and salinity to calculate the density. So the obstacle, in a sense, to recreating, to studying past ocean currents is actually the lack of information about the sea surface height before 1993. So we use this method called the Bernoulli inverse. And I'm not going to go into too much detail about how it works, but suffice to say it is a mathematical trick for generating sea surface height from the temperature and salinity data. So this allowed us to look at sea surface height before the satellite era, and therefore look at the barotropic flow. So we can therefore look at the barotropic flow and the baroclinic flow before 1993. So this figure here shows the sea surface height in the North Atlantic. On the left is from the Bernoulli inverse solution, and on the right is from the satellites. We can see that the Bernoulli inverse solution doesn't get a lot of the fine scale detail, but it does get the large scale structure of the sea surface in the North Atlantic correct. So, and that's useful for studying the large scale currents which make up the AMOC. So what we did was we took this Bernoulli inverse solution together with the density measurements, and we reconstructed the currents over the last 120 years. And from those, we could calculate the strength of the AMOC over the last 120 years. So this is what we got. This is a paper we recently had accepted in Geophysical Research Letters, and it's 120 years of AMOC reconstructed from observations using the Bernoulli inverse. And this top panel here shows the change in AMOC over that time. As you can see, it wiggles up and down quite a lot. There's a lot of variability, but probably most strikingly, there's no evidence of a 20th century AMOC weakening. So there's no significant downward trend in this. The AMOC has been in a weakened phase over the last 10 years, though. However, when we plotted our AMOC strength record alongside the sea surface temperature signal that I introduced in slide 1, we did see a close relationship between the two, and found strong evidence really that this sea surface temperature signal is being driven by changes in the AMOC. So this could potentially help climate prediction in two ways. Firstly, if we keep measuring the AMOC as we are using the RAPID and OSNAP and others, that will allow us to predict the sea surface temperature in the short to medium term. So this is not so much about long-term climate change as the ability to predict climate variability. And as we know, sea surface temperature is strongly linked to extreme weather events. So if we can predict sea surface temperature in the short to medium term, that would hopefully increase our preparedness and resilience against extreme weather events in the continents surrounding the Atlantic. The second way that this could help prediction is ground truthing models. So we saw that there was a huge spread in what the different models say the AMOC has been doing over this time. So if we can get the models to successfully reproduce this behavior and crucially reproduce this relationship between AMOC strength and sea surface temperature, then those models can be better trusted to predict the AMOC over the coming century. So what about this cold, fresh blob in the North Atlantic that I showed in the first slide? Well, what happened here is that the salinity south of Iceland, it's suddenly got colder there. It also got fresher, so it lost salinity in the last 10 years. We can see the salinity south of Iceland here. So since 1900, the salinity was fairly stable. And then in 1970, we had the sudden drop in salinity. This is the Great Salinity Anomaly. It gradually recovered after that. And then now we're encountering this situation, which is, if you like, an even greater salinity anomaly. So a paper by my colleague at the NOC, the National Oceanography Centre, Penny Holiday, did a good job of explaining this. They looked at observations and found that the wind patterns changed over the North Atlantic in this time. And that really changed the direction of the currents in the upper part of the AMOC. So the warm water traveling northwards, it stopped taking this northern path, which takes it close to the middle of the Atlantic. And it started more taking this southern path, which takes it sort of skirting around the edge of the subpolar North Atlantic and closer to Scotland. And at the same time, cold, fresh Arctic water was redirected into the middle here. So this is, we don't think, linked to a kind of long-term weakening of the AMOC. It's not caused by that, but it did coincide with a weakened phase of the AMOC in the last 10 years. So these two things together have acted together to cause this. However, the low salinities that have resulted from this are likely to slow the AMOC down in the future, because as I said at the start, the AMOC requires cold, salty water. That's how we get this dense water formation. If that water is much fresher, then we won't get the same dense water formation and the AMOC will slow down. So I'm just going to go one more slide just to summarize and conclude. Back to my original question, what is going on in the North Atlantic? Well, this warming at below the global average shown here, or even cooling, we think this is maybe just as likely caused by a change in the AMOC structure as it is in strength. It's certainly not unlikely to be due to long-term decline in the AMOC, perhaps more likely just that the pathways of the warm water have changed. However, the low salinity we have here, so this is temperature, but it's also low salinity here, is very likely to cause weakening in the near future. And that's also what the models suggest is going to happen in the future. This 70-year time series, 70-year variability in surface temperature here, we found that this is very likely to be driven by the AMOC. And as a kind of final take-home message, we need to keep measuring the AMOC. If we keep measuring the AMOC, then that will improve our ability to predict these fluctuations in surface temperature in the short to medium term. So I'll end there. Thank you.
Right, Neil, thanks very much. Very interesting and obviously a very important issue. Now, we come to Q&A really and discussion. I'm going to suggest that we deal with questions that come in on Neil's talk first and then go back to Pete's talk. We've got quite a lot of questions on nature-based solutions, so we'll try and do them in two sections. There's an interesting question from Melvin Cannell. Will the AMOC tipping point have been passed once weakening has been observed? In other words, will we know it when we see it?
So, well, that's a difficult question. There has been a lot of research recently. A big paper came out earlier this year about the idea that the AMOC it might surpass a tipping point after which it won't recover. So there has been theoretical work showing that the AMOC is a kind of a bistable system, if you like. So it will flip between a kind of a high and a low phase. And once it flips to the low phase, it might be very hard to get it back up to the high phase. The research that came out earlier this year, in quite a major paper, was looking at all these proxy records, which I showed, and maybe some others, and doing some statistical analysis on them to show that the AMOC, that if you model it as a kind of a linear system, then the relaxation rate of the system is weakening. Basically, it's going further and further out of equilibrium. However, I suppose, I think that's a major result. But my one reason to be wary is that they're looking at these proxies and maybe slightly assuming that these proxies are purely representative of the AMOC, whereas there's perhaps a lot of other information in those proxies as well, which is not related to the AMOC. So it's a difficult one. I don't know if the AMOC has passed the tipping point yet.
Yes. David McDonald asks, is any of the cooling in the North Atlantic related to Greenland glacial ice melt?
So that's a great question. And the answer is, it doesn't look like it, no. I think that the Greenland ice melt has obviously contributed to increased fresh water in the North Atlantic, but it's still a relatively small term in terms of the total freshwater budget in the North Atlantic. However, talking about tipping points, there is, if the Greenland ice sheet was to suddenly rapidly lose mass, which it has perhaps started to do, then in future we might expect a very large effect on the salinity of the North Atlantic from that, and that would have huge effects on the AMOC as well. So yeah, the Greenland ice sheet, that is a concern. I don't think it's really reared its head yet in terms of the effect on the ocean circulation.
Tiffany Laws asks, recent droughts in Scotland, is it possible to look at the AMOC in these years against droughts in Scotland? Is there any relationship?
It would be possible. I'd be wary of looking at AMOC variability with regards to specific years. I think AMOC variability is it's a longer term thing, and so there will be interannual climate and weather change in weather, which will be kind of on top of AMOC variability. So I would be wary to attribute it to the AMOC directly, but it would be perhaps worth looking at.
And then David Fowler has asked, what is the physical reason for the consistent modelled future AMOC weakening?
Well, I'm not a modeler, so I'm not going to be able to answer that question fully. There's these models. These are climate models, so ocean and atmosphere models, where they run several different simulations. Well, lots of teams throughout the world run several simulations, and they force their models with different levels of emissions, and they all find this behavior. But it's not always that easy to directly attribute one thing to another in the models. They're complex systems. So in effect, that's why we use the models. We can just switch things on and off and see what happens to the AMOC. The AMOC is something that the models struggle to get it right. So there's a bit of uncertainty in that, I suppose. Sorry, that's not a very complete answer, but it's a bit of they're a bit of a black box as far as I'm concerned.
Yeah, I mean, I think we can appreciate this is a very difficult issue. Last question for you, Neil. Hannah Thompson asks, if we manage to achieve the climate goals, will water naturally become more saline than fresh, or do we have to do more to get the whole system back to normal again?
So I suppose this is in relation to the sudden freshening of the North Atlantic in the last 10 years or so. As I say, that's really caused by a combination of change in the wind conditions and kind of the AMOC being in a weakened phase. But can't really say what those wind conditions are going to do in the next 10 years. They could revert back to what they were and start steering lots of warm, salty water back into the interior of the subpolar North Atlantic there. So again, there's lots of things going on over different timescales here. If the AMOC continues to weaken, we would expect to see less warm and salty water flowing into the Atlantic. If we and it is likely to continue to weaken even in the low emission scenarios.
Okay, that's interesting. Right. Well, thank you very much, Neil, and all the best with your research. I think that's very challenging.
Thank you.
But very important work. I'm very pleased to see that the rapid array is still going on as well, because I remember when I was working about 20 years ago, it was just being set up. So that's great stuff. Now, I think we should turn to the talk from Pete Smith on nature-based solutions, and we've had quite a few questions about this. And I think there was a general question which I'm just looking for. I suppose there's an underlying question that quite a few people have asked, is that is it actually a long-term solution to use nature-based solutions? I mean, can we rely on it? After all, trees die, they burn, and so on and so forth. Is this really very viable as something that you could rely on?
Yeah, that's a really good question. So as I mentioned in the talk, biological sinks are reversible. So if you change soil management practices to increase the soil carbon, and then you reverse them later, you lose all of that soil carbon that you've gained. And with trees, it's reversible as well, because if you get a pest and disease outbreak that sweeps through the trees, like ash dieback, or like some of the red band needle blight that we've had in Scotland recently, then we could lose a lot of the vegetation carbon. So we have to think about that, and we have to think about future-proofing them against future climate change and future outbreaks. So there's that issue of reversibility. There's another one, which is saturation. So when trees grow to their maximum height, they store a lot of carbon, of course, that they've accumulated during growth. But then the carbon coming in through photosynthesis is equal to the carbon going out through respiration. So they're no longer storing additional carbon from the atmosphere when they reach maturity. So those are two of the limitations of biological sinks, and all nature-based solutions really work by biological sinks. So we have to consider those. But I think that they're really important, particularly with our net zero targets for 2045 to 2050, because whilst we're decarbonising the rest of society, we can use nature-based solutions for greenhouse gas removal. So our targets are going to be extremely difficult, extremely challenging to meet anyway. But if we have nature-based solutions for the next 30 years, those sinks are still going to be growing, and they're still going to be reliable over the next 30 years at least. If they do start to get reversed over time after 2050, we can start to manage that, because we've largely decarbonised society by then, all of the other sectors of the economy, and we can start to manage that. We can start to manage that risk, I suppose. And the other question that came up in the chat that I saw that could address this is that we could harvest some of that timber and use it in long-lived products. So, for example, if we use more timber in construction, we currently import a lot of our timber for construction. If we grew that domestically, it would be good for our local economy and would be good for storing that carbon in longer term pools, which would maybe last several hundred years. So there are a bunch of ways that we could get over those risks, or that those risks could be managed, but they do have to be considered against longer term storage. We need longer term storage as well. But I think that to hit our net zero targets by 2045 or 2050, nature-based solutions can play a significant role.
Okay, thank you. There's a question from Hugo Talbot, which just disappeared from my view. As more questions come in, they move about. I mean, basically, he's asking, will the effectiveness of nature-based solutions depend on how climate will actually change? So, in other words, the future scenario will affect the viability of the nature-based solutions, perhaps.
It can do. It can do. In some cases, it could make nature-based solutions more effective. So if we get increased temperatures at northern latitudes, that could improve productivity and could improve growth. So it could actually improve the drawdown that we get from the atmosphere. That could improve the rate of carbon sequestration. On the other hand, if we get more extreme events, we could be losing more trees if we're using trees, or more other ecosystems to store carbon. We could lose more of that to wind throw, to future fires, to extreme storms. So again, it comes down to that, managing the risk of the vulnerability of biological carbon sequestration. We have to, not all of the forest stock is going to disappear, but a certain proportion of it may, and that may be increased with increasing extreme events. So you have to try and future-proof it, and that could be done by managing the planting structure of a mixed forest in a way that would give it shelter. So risk management is really important. It's similar answer to the first one.
Yes. Okay. Thank you. Malgorzata Stanton asks about basically the incentivization of Scottish agriculture to improve the sequestration. Could carbon credits or something be used to award farmers?
That's a great question. Thanks, Gosha. Nice to see you on the call. So yes, that it could be. I mean, Scottish farmers or UK farmers are crying out for these other sources of income that would help them to make the right management decisions to manage their land. The big problem at the moment is the monitoring, reporting, and verification of soil carbon. So how do you, in order to sell your carbon credits, you have to be able to demonstrate that you're actually getting that carbon stored in the ground. And at the moment, that's very difficult because you've got a very large background stock of soil carbon, and the increase in soil carbon is relatively small compared to that large background. And unlike trees, where you can go and measure, you can just put a tape measure around them and measure the height, you can see them growing. You can't see changes in soil carbon stock. So there are proposed methods to improve that monitoring, reporting, and verification system, which involve remote sensing, measurement, modelling, repeat surveys, but that's not as yet operational. And I think that's the next big step that could unlock the potential for carbon sequestration in soils. And that's something that we're working on at the moment.
Excellent. Okay, thank you. I'm just quickly looking at some of the other questions that have come in. There was a question about the value of trees versus moorland, which I take to mean peat. Which is the more important thing to be? Well, I mean, presumably we have to do both. We have to protect both forests and lands, but relatively speaking, how important are?
Well, you do. So if you've got a degraded peatland, the most effective solution is to restore that peatland, to re-wet it and to revegetate it. You switch off a very big source. Degraded peatlands can be a source of up to 30 tons of carbon dioxide equivalents per hectare per year. That's many times more than the average family car emissions in a year. So you can immediately switch those off by re-wetting, and you can eventually convert those peatlands into a net carbon sequestration opportunity. So that's with a degraded peatland. Definitely don't plant trees on it. Restore it. You can plant trees on mineral soils. The grey area is the organomineral soils, so where you have a very shallow layer of peat. And some of our recent research has shown that you can lose more carbon from the shallow layer of peat than you gain in the vegetation. So that's the area where it's a bit of a grey area, and you need to be really careful with afforestation of those areas. But mineral soils are good for afforestation. Degraded peatlands are good for peatland restoration. We need to do both, but we can't do them both in the same place.
I'm good to. I think that's great. What I just want to do now is sort of open the discussion to a more general level. Actually, there's a question from Alex Chandley, I think it is, and if Neil is still around, he can come in on this as well. Indeed, the others. And this is quite a long question, but I think it's an important one because I think it's something important for all scientists. Considering the apparent recent increase in public receptiveness to tackling climate change, where do the speakers recommend appreciate the tone of scientists on the scale of climate catastrophe to drive discussion, e.g. increasing use of alarm-raising statements in scientific literature, or the heightened tone of this summer's IPCC reporting prompting the UN Code Red announcement that had non-scientists asking me about this change in discourse? So, are scientists to drive when they talk about climate change? Do they need to be a bit more extravagant in their language in terms of impending catastrophe and doom? I'd like to know what your views on this are. Thank you.
So I think we've got to tell it like it is. I think it's our job to tell it like it is. And if we see, our government, the UK government, the Scottish government have declared a climate emergency. They recognise that this is an issue that we have to solve. We have to solve it within the next decade, and otherwise there's going to be some really significant and dire consequences around the world. As scientists publishing papers, we maybe just put out the data that the people who then sound the code reds draw on. But I think it's important that we give those messages. There's a fine line between providing the evidence and climate change advocacy. But I've got down off the fence in recent years because I think it's too important not to say we need to act, and we need to act really quickly.
Gabby, do you wish to come in on this? Yeah.
I totally agree with Pete. I think it also depends on what role we are speaking in. If we, for example, work on an IPCC report, it is very important to be objective and to look at all the evidence and to not let our personal views or concerns and worries affect what we write and how we conclude. So science has to be objective, and we are both sides. It's very different from, for example, a lawsuit where you argue as one side strongly. Science argues both sides at the same time, and we are our own strongest critics. But then I have to admit that my own watching this unfold and watching how dangerous it's starting to look, I just can't step back anymore to the extent I did maybe 10 years ago. It's just too worrying to me. And I think it is important to also say so, but I have to separate very clearly that I'm now speaking as myself, that I'm worried, but it's up to the governments to make the decisions. But I have a view of what those should include.
Neil, do you want to add to that? No, it's disappeared.
No, I'm in complete agreement with those answers. Great answers, and yeah, completely agree.
Can I ask you whether you feel that you think you are being listened to, actually, and whether politicians and those who have got responsibility for making changes are actually really listening to the science?
More so than 10 years ago. 10 years ago, I think we were still making the argument, you would still give a talk and you'd get climate deniers showing up at the meetings. That the dialogue has completely changed now. People aren't asking whether it's real or not. They're asking, what can I do to solve the problem? So I think that the narrative has changed, the conversation has changed, and that's my experience. But I'll leave it over to others now.
Yeah, I totally agree that there's really a change, which is encouraging to me. Also, the Fridays for Future have made a difference. I think it has just brought out this public concern in a way that is really unique. And I think Greta Thunberg has done something amazing there, because it was simmering, but it needed somebody to bring it out. And so in many ways, there's good signs that this is a public concern now. It is always tricky when it starts to cost, when we have to make decisions that are not the easy decisions. So not the win-win ones, but the trickier ones, which we also will have to make. And so I think it will be a difficult discourse how we make sure that it hits the costs of a transition, which could be a transition to a really interesting, sustainable, and good way to live. But it is a transition, and transitions have always been difficult, and some people suffer from them, and we need to figure out how these costs are carried. And as that unfolds, you will see advocacy groups for various ways to do this come out, and they don't always necessarily say what they are trying to do, but they use arguments that they think are helpful. And so this is why I also was a bit worried about the tack towards personal responsibility, because this isn't solvable by personal responsibility alone. And I think there are some interesting interests pushing the argument of the personal responsibility, while we really want to act right as people, but we need the frameworks to be able to do the right thing, and that needs a strong government action.
Yes, good. Thank you very much. Now, I'm just going to wrap this up in a minute, but I had a question which I need to find, and it's going back to my talk this morning about the COP. And James Curran asks, there's about 100 companies that contribute 70% of climate emissions. I'll take your word for that. Should there be a big business group at the COP? So this is the question, the role of the private sector versus the role of government, really. Ultimately, the COP is about governments discussing what their actions are. But it's very interesting to note that something which was introduced in Paris was a very strong element of engaging with the business community and getting them to come up with solutions and to think about what they can do. And I think that's increasingly going to be the case. Obviously, there isn't a role in a formal sense for businesses to negotiate, but they are very much represented in meetings at the COP, and they will lobby and they will talk to people. But I think more importantly, governments now recognize that you can't just deliver the solution to this by government action. It doesn't involve the whole economy and everyone who plays a major role in that. And I think that's the way it's going to have to change. I mean, one of the things that I've always felt was that as soon as a new technology, which is, let's say, low carbon, becomes effective and cheap relative to carbon-based, then it will happen anyway. It will happen very quickly. And I always look at the of digital cameras. No government said you should own a digital camera, but I doubt if very few people actually use film nowadays. And so things can change very quickly once the technology is there. And what government's role is to ensure that things are pushed along faster than they would happen naturally in a goal-orientated setup. So that's how it looks to me. Certainly, businesses are heavily engaged in meetings of this nature, one way or another.